In the previous class, we have discussed about the electronic configuration of the transition elements. Here in this case, we will be discussing about the anomalous electronic configuration of d block elements. We can generalize the outer shell electronic configuration as n minus 1 d orbital can take electron from 1 to 10 and outer ns orbital can take electron from 1 to 2. We have observed many exceptional cases. In the 3D series, we have observed for chromium and copper we have exceptional electronic configuration. In the similar way, in the 4D series, we have anomalous electronic configuration for niobium, molybdenum, ruthenium, palladium and for silver. In the case of 5D series, we have observed the anomalous electronic configuration for platinum and gold. These are the two elements in the 5D series have anomalous electronic configuration. We need to know the reason. As I said before, off-filled and completely filled electronic configurations are stable. What is the reason for this stability? Here are the reasons for anomalous electronic configuration. That is a symmetrical distribution of electrons. That means symmetrical uniform distribution around the atomic orbital. So when we have symmetrical electronic configuration like off-filled, in the case of off-filled electron, there will be 5 electrons in the inner d orbital. These 5 electrons will be arranged symmetrically in order to minimize the repulsion among the electrons. Here we have these 5 electrons will be arranged symmetrically in the d orbitals so that there will be a minimum coulombic repulsion between the electrons. Next reason is higher exchange energy. To know this, we need to know about the exchange energy. Now see what is meant by exchange energy. Energy released when two or more electrons with the same spin in a degenerate orbital exchange their position in the same subshell. This is nothing but electrons with the same spin in the degenerate orbital. As we have seen, these d orbital will be having 5 degenerate orbitals. In this, the electrons are filled. So when these electrons of the spins are having same spin, these 5 electrons exchange within the degenerate orbital within the same subshell. This is the, if these electrons can exchange with the second, this electrons can also exchange with the third one. This electron can exchange with this electron and this electron can exchange with this electron. So these electrons with the same spin will be exchanging in their orbit. That time energy will be released. If you have the electrons in the 5 different orbitals with the opposite spin, you may consider there are 2 types of electrons in this. We have 5 upper spin electron and the one which is having lower spin electron. Lower spin electron can't exchange with the upper spin electron. This is not possible. If the electrons with the upper spin electrons can exchange only with the upper spin electron and the lower spin electron can exchange with the lower spin electron like this. So this lower spin electron can exchange with the lower spin electron of the second subshell. In the similar way, lower spin electron of the third subshell. Here we don't have lower spin electron. These electrons can't exchange with these 2 electrons. So in the similar way, if this lower spin electron can also exchange with the second or with the first like this, these electrons will be exchanging in the atomic orbital. During this, energy will be released. Electronic configuration which releases more amount of energy which will get higher stability. So energy released can be expressed as energy exchange energy. E exchange will be equal to K into P. So K is the exchange energy constant. K is nothing but constant, and P is number of exchanges, possible exchanges, number of exchanges. So this P can be written as, P can be given as n factorial divided by 2 into n minus 2 factorial, where n is the number of pair of electrons with the same spin, same set of electrons. Now we will calculate the exchange energy for chromium. With the atomic number 24, we have written the electronic configuration. We have two different types of electronic configuration. One is observed and another one is expected. This is for observed electronic configuration, and this one is for expected. So what is the electronic configuration? 4s2 3d 4 is the expected configuration, and but which is not true. The observed is 4s1 3d 5. Now we will see how to calculate the number of exchanges. See here, the 4s orbital will not be involved in exchange energy, as this s orbital do not have degenerate orbital in both the cases. So only d orbital is involved in exchange energy. The first electron can exchange with the second electron, similarly with the third, because all these electrons are of same spin and in the same orbital. So we have 4 exchanges for the first electron. The similar way for the second electron, you can see here, first exchange, second exchange, third exchange. So here we have 3 exchanges. You may ask the question that the second electron can exchange with the first, but we have already taken into count which is similar to the first electron which is exchanging with the second electron. So that's why we have neglected. We have 3 exchanges. In the similar way, for the third electron, 1 exchange. There are 2 exchanges for the third electron. That means third electron can exchange with the fourth and fifth, and similarly exchange with the second and first are already taken into count. And the fourth electron can exchange only with fifth electron. Here we have 1 exchange. If you count the number of exchanges, that is P is equal to 10 exchanges. If you calculate by using the same formula, that is P is equal to n factorial divided by 2 into n minus 2 factorial. Number of electrons of the same spin are 5 factorial divided by 2 into 5 minus 2 factorial is 3 factorial. If you simplify this, 5 into 4 into 3 factorial divided by 2 into 3 factorial, it get cancelled. 2 1s are 2 2s are, then you will get 10 exchanges. So we have counted the exact number of exchanges. So we have got the P value. Exchange energy formula is energy of exchange will be equal to K into number of exchanges, that is P. So K into 10. So that means 10K amount of energy will be released when the chromium acquires a filled electronic configuration. Let's see the number of exchanges and exchange energy in the case of expected electronic configuration of chromium. First electron can exchange with the first, second and third. In the similar way, second can exchange with the third and fourth. So 3 plus 2 exchanges. The third electron can exchange only with the fourth electron. We will be having only 1 exchange. So number of exchanges will be equal to 3 plus 3, that is 6 exchanges. Total 6 exchanges. Exchange energy will be 6K. So here we are getting 6k amount of energy, whereas in case of off-filled configuration we are getting 10k amount of energy. That's why 3D5 configuration is more stable when compared to 3D4 configuration. Next, we'll take one more example, that is copper. This one is for observed and this one is for expected. As we expected, 4s will take 2 electrons and the 9 electrons will be in 3D orbital like this. So here in the observed electronic configuration we will be having 10 electrons in the d orbital and 1 electron in the 4s orbital. Here we have two types of electrons, that means upper spin and lower spin. So I have said before, only upper spin electrons can exchange with the upper spin electrons and lower spin electrons can exchange with the lower spin electrons. We have 5 upper spin electrons. For 5 upper spin electrons, number of exchanges will be 10 exchanges. For the lower 5 lower spin electrons, you will get another 10 exchanges. So total will be 20 exchanges. Here we have 5 upper spin electron and the number of exchanges for this 5 upper spin electrons will be 10. We have 4 lower spin electron. For this, if you calculate 4 factorial divided by 2 into 4 minus 2 is 2 factorial. If you calculate the value of number of exchanges, 4 into 3 into 2 factorial divided by 2 into 2 factorial, get cancelled, 2 ones are 2 twos are 2 into 3, 6 exchanges. Number of exchanges will be 6 for the lower spin electrons in the expected configuration. The total number of exchanges will be 16 in the case of expected electronic configuration. Exchange energy for this is 16k. For the exchange energy for the observed electronic configuration is 20k. So higher the exchange energy, stable will be the electronic configuration. That's why these gets extra stability by acquiring higher exchange energy. Now we will see the characteristic features of transition elements. As we have seen in the periodic table, metallic character varying from S block to P block, as these D block elements are kept in between S and P block elements. These are called as transition elements, and we have seen the electronic configuration of transition elements. These have partially filled d electrons. D block elements have unpaired number of electrons. These acts as a good conductors for heat and electricity. That's why these are called as metals. And these transition metals will be having higher melting and boiling point. And these transition elements are lesser in nature, that means reflecting property of light. They can reflect the light which is falling on the surface of the transition elements, and these are malleable. So malleable means the property which withstand the hammering, so that we can make into sheets. We are using gold plates, platinum plates, malleable property of the transition elements, and these are ductile in nature. We are using copper wires is because of the ductile nature of copper. That means these transition elements can be drawn into wire form, and these transition elements can form metal alloys. Gold that we are using is not the pure gold which is mixed with some amount of copper. So these can form alloys. Because of the presence of unpaired electrons, these shows variable oxidation state. Because of the presence of partially filled d electrons, these shows variable valency or variable oxidation state. Because of the presence of these unpaired electrons, these can absorb the energy from in the visible region, so that these can exhibit or these can form colored complexes. Because of these unpaired electrons, they are magnetic, ferromagnetic, these transition elements shows magnetic property because of the unpaired electron. Transition elements shows magnetic property because of the partially filled d electrons or the electronic configuration. These have unpaired electrons, these have completely filled d orbitals. That's why they show magnetic properties. In the similar way, because of the property of showing variable oxidation states, these can form a intermediate compound and intermediate unstable compounds, so that these transition elements can be used as a catalyst in several reactions.